The different chromatography techniques all achieve the same thing. That is, that they separate the mixture out into its individual components. And we can get some idea of what some of the components might be by comparison to authentic samples. But to really confirm, sufficient for a court of law, what those components are, we have to have some more techniques. We have to positively identify those components and say absolutely what they are. And to do this, we can use spectroscopy and spectrometry. The kind of spectroscopy that is most useful for the identification of compounds for forensic purposes is infrared spectroscopy. Now, infrared spectroscopy is based on molecular vibrations. Now, when we look at diagrams of molecules in textbooks, we always think of them as rigid things, rigid objects, but they're not. Molecules are flexible. The bonds connecting the atoms, they stretch and they bend and they wobble. And the energy changes that correspond to all these movements match the energy of infrared light. So if you take a molecule and you irradiate it with infrared light of the correct frequency, then it will start to vibrate. And it's monitoring the absorbance of infrared light that is the basis of infrared spectroscopy. Now, if we take a simple molecule where you have two atoms connected together by a bond, this behaves very much like the classical simple harmonic oscillator. And the frequency with which that molecule will vibrate, the bond will stretch backwards and forwards, depends on two things. It depends on the masses of the atoms involved, and it depends on the stiffness of the bond. Now, chemical bonds in organic molecules come in three types: single bonds, double bonds, and triple bonds. Single bonds are less stiff than double bonds, and triple bonds are the most stiff of all. So we can use these very simple concepts to look at where in the infrared part of the spectrum different molecules or different parts of molecules will absorb infrared light. So this is the infrared part of the spectrum. For historical reasons, chemists use a very odd unit to measure the frequency of infrared light. They use the inverse wave number, centimeters to the -1. And the infrared spectra of organic compounds are typically recorded in the range of 600 to 4,000 wave numbers, inverse centimeters. Now, when we look at the left-hand part of the chart, we can start to group together particular types of bonds. For instance, oxygen to hydrogen bonds, nitrogen to hydrogen bonds, and carbon to hydrogen bonds are all on the far left-hand side. And you can see a small difference between the OH, NH, and the CH bonds. These are all in that particular position because they all involve the lightest atom, which is the hydrogen atom. The stiffest bonds, that is the triple bonds, and whether they're triple bonds between carbons or nitrogens or oxygens, they're all in roughly the same place, and that's at approximately 2,000 wave numbers. Not quite so stiff are the double bonds, carbon-oxygen double bonds, carbon-carbon double bonds, carbon-nitrogen double bonds, and these are all grouped around 1,600 to 1,800 wave numbers. You'll notice that all of these are in the left-hand part of the spectrum. They're all above 1,500 wave numbers. This region of the spectrum is characteristic of the class of compounds. So if you look at the information from the part of the spectrum above 1,500 wave numbers, it tells you about the class of compounds to which your sample belongs. It's not very helpful at telling you which specific compound in that class your sample is. So above 1,500 wave numbers, it's a very useful region for research chemists. But it's not a very useful region for forensic scientists because forensic scientists want to individualize their compound down to one particular one. That is best done on the right-hand half of the spectrum, below 1500 wave numbers. In this part of the spectrum, you have all the single bond vibrations. You have all sorts of bending modes. You also have all sorts of complex deformations. It's a very complex part of the spectrum. But this means that the spectrum you record below 1500 wave numbers is characteristic of a specific compound. In fact, this part of the spectrum acts very much like a molecular fingerprint. So if you take the infrared spectrum of your unknown compound and you look in this region and you compare it to the standard sample, the infrared spectrum of the standard sample, and those two match, then you've got a very strong identification of that compound. Here's an example. It's an infrared spectrum of diamorphine, which is the active ingredient of heroin. And if we look on the left-hand half of the spectrum, which is outlined in red, you can see a series of bands. And if you look closely at that part on the left-hand side, it tells you about some of the parts of the molecule. For instance, we can see that this molecule has ester groups. We can see that it has carbon-hydrogen bonds. But there's nothing in the left-hand half of the spectrum that tells us this is diamorphine. It simply says this has some of the chemical functional groups that diamorphine also has. It's only when we look at the right-hand half of the spectrum outlined in blue, the so-called fingerprint region, that we can say this is diamorphine. It's, as you can see, it's very complex, it's very rich in detail, and comparison to an authentic sample proves that this is indeed diamorphine.